When we compute the double integral, sometimes we must divide the integration domain into two or more parts. Let me illustrate this by the following example. Consider the function fxy being x times y, and the integration domain D is the set of all pairs xy from R2, such that x is between 1 and 2, and y is between 1 over x and x. First, it's a good idea to sketch the integration domain. X goes from 1 to 2, and y is bounded by these two functions. 1 over x is a hyperbola, like that, and y is equal to x is a straight line, this one. And for x between 1 and 2, y should be between these two curves. So this is the domain of integration. For 1 we have 1, for 2 we have 2, and for 2 we have 1/2. So we can write the integral over the set D of the function fxy dx dy, and we want to try both orders of integration. Let's start with this one, when x goes from 1 to 2, and y, for each x between 1 and 2, say this one, y starts at the hyperbola, that means 1 over x, and y goes up to the point on this line, y is equal to x. That's it. Well, and now we can compute this integral. So when we integrate y dy, x is a constant, and we can factor out this constant in front of the first integral. And integral of y dy is 1/2 of y squared, so we can factor out 1/2, and we have y squared alone. And y goes from 1 over x to x. So we have integral from 1 to 2, x/2, and now when y is x, we have x squared minus, and y is 1 over x, we have 1 over x squared. We can factor out 1/2 in front of the integral, and we have integral from 1 to 2 x cubed minus 1 over x dx. So the antiderivative is x to 4 divided by 4 minus logarithm of x from 1 to 2. Let me write it here so that we have some space here for the second way of computation. So we have 1/2 of, when x is 2, we have 16 divided by 4 is 4, minus logarithm of 2, and when x is 1, we have 1 over 4, and logarithm of 1 is 0. So we have 4 minus 1 over 4 is 15 over 4, So we have 15/8 minus 1/2 of logarithm of 2. (15/8 minus 1/2 of logarithm of 2). Okay, this is the result. This is the integral. And let's try to reverse the order of integration. Can you try yourself? Stop me for a moment and try it yourself first. Okay, ready? Well, if not, let's try together. This time, we cut the integration domain in this way. Now, y runs from 1/2 to 2, but the left border consists of two simple curves. Each of them is simple enough, but it's not easy to write a common formula for these two curves. In these cases, we want to split the integration domain into two parts, the upper part and the lower part, because then in each of these two parts, even the left border will be easy to describe. So instead of integrating over y from 1/2 to 2, then we integrate from 1/2 to 1 plus from 1 to 2. This is over y. And then for each y between 1/2 and 1, x starts here. That means x starts at 1/y and it goes up to 2. And in the upper part, for each y between 1 and 2, say this one, x starts at this line, that means at y, and it goes up to 2. This is the common right-hand side border. So we have to compute these two integrals and add the results, hopefully to get the same result as before. Okay, let's try. So we have integral from 1/2 to 1. When integrating xy dx, we can factor out y, and integral of x is x squared half, so we can factor out y half, and the antiderivative is x squared for x starting at 1/y, going up to 2. Plus, and the second integral is from 1 to 2, and then we integrate the same function. So this will be again x squared half. We can factor out y half, but the limits are different. Now x starts at y instead of 1/y, and it goes up to 2. Here, when x is 2, x squared is 4. When x is 1/y, x squared is 1/y squared. So this is the integrated function. When we expand this multiplication, we have 2y minus 1/2y And then the antiderivative is y squared minus 1/2 logarithm of y from 1/2 to 1. Which is 1 minus 0 minus, and when y is 1/2, we have 1/4 minus 1/2 of logarithm 1/2. And for the second integral, we have x squared at 2 is 4. Sorry, this is something wrong. Y, x goes from y, x starts at y, and x goes up to 2. So we have 1/2 times, when x is 2, x squared is 4, minus, and when x is y, x squared is y squared. So the integrated function is 2y. This is similar as before, but then instead of 1/2y, we have minus y cubed half. So the antiderivative is y squared minus y to 4 divided by 2 times 4, which is 8, from 1 to 2. When y is 2, we have 4 minus 16 over 8 is 2 minus 1 minus 1 over 8. And when we add these two results, we hopefully get the result as before. So here we have 1 minus 1/4, which is 3/4. And logarithm of 1/2 is minus logarithm of 2. Second minus, third minus, so we have minus 1/2 logarithm of 2. Let me check this with my previous computation. Yeah, 3/4 minus 1/2 logarithm of 2, right? And this is 4 minus 2 is 2, minus 1 is 1, plus 1 over 8. And when we compare this to the previous result, minus 1/2 of logarithm of 2 is here, minus 1/2 of logarithm of 2 is here. And when we bring these two terms to the common denominator, which is 8, then we have 6 plus 8 plus 1, which is, yes, indeed, 15 over 8. So, yes, this is as before, 15 over 8 minus 1/2 logarithm of 2. In some cases, one order of integration may lead to the result, while the other is not possible. In simple cases like that, sometimes both ways can be used to give the result. But as you can see, sometimes, due to the heterogeneous nature of the left-hand side border, we had to split the integral into two to be able to write the starting value of x as 1 over y for this part, hyperbola, and y for this part being on a straight line.